Good evening to all. Okay, so lecture sections will be added. Okay, I'll ask the people to add. Fine. So let us start with today's topic. So today we're going to see about dynamic programming. In the last class we saw greedy strategy, right? Okay, so in the greedy strategy, what did we do? We just at present, whichever is the optimal solution that we consider as the correct solution, and then we proceeded, right? Okay. So whereas in dynamic programming, we're not going to do that. So we are going to like store all the past solutions and keep, and then use them to solve the current solution. Okay. So that is called memoization. So it's nothing but you're going to store all the past solution. Okay. So whatever solution you got, you'll be storing it somewhere, and then you're going to use that to solve the current solution. Okay. So that past solutions, we cannot store all the past solutions, right? So only if that particular solution is the most optimal solution, then only you will store that. Okay, so it is nothing but storing the suboptimal solution. Okay, storing the suboptimal solution to solve the or to get the present solution. Okay, We'll be seeing examples, okay? Then you'll understand. Okay. So one best example for this dynamic programming is the Fibonacci using recursion we saw on code, right? While doing recursion. Okay. So to solve the Fibonacci series, we had a tree kind of a structure. So to solve Fibonacci of 5. So what was the tree structure? To if you want Fibonacci of 5, we need a Fibonacci of 4 and Fibonacci of 3, right? So for f of 4, we need f of 2 and f of 3 and f of 2. And for f of 3, we need f of 2 and f of 1. And for f of 2, we need f of 1 and f of 0. Right? And again, for this f of 2, we need to calculate, sorry, f of 1 and f of 0, right? And again, for f of 3, okay, for f of 3, again, we need to calculate f of 2, f of and 1. And for f of 2, we need f of 1 and f of 0. You see here, one thing to be noted is this f of 2 is already calculated. Okay, even though it is already calculated, what we're doing? We're doing the same calculation once again. So here, see here, if f of 3 is there. So for calculating f of 3, already we have done these many calculations. Again, for finding f of 3, we're doing the same calculations once again. So you can see a lot of repeat happening, right? Okay, so actually what we can do is, instead of calculating f of 3 again, we can store this f of 3 somewhere, and then we can check whether it's already calculated or not. Only if it is not calculated, we're going to make the recursive call. Understood? So we're just going to maintain an array which will store all the values that are already calculated. Okay. So size of this array is going to be the Fibonacci number which you're going to calculate plus 1. Okay, because 0 also included, right? Okay, f of 5 means from 0 we need till 5. So totally 6 elements are needed. Okay, I'll write from bottom to up. So f of this table is going to store the values. So initially I need to store some value, right? I have to initialize with some value this array. So initializing this array, like what you have to do is you have to store a value which is not a Fibonacci number. Okay, if you store a Fibonacci number, what happens? It thinks that is already calculated. Okay, then it will not proceed to the further calculations. So what you have to store here is we have to store a number, a default number, which is not a Fibonacci number. Okay. So just for simplicity, we can store -1. -1 is not a Fibonacci number and it's also a negative number. So we can give -1. And so this 1 and 0 are going to be our base conditions, right? Okay. So we can mark them as already found. What can we do for that? We can store the original values itself. Okay, Fibonacci of 0 is 0, Fibonacci of 1 is 1. Right? So I'm making f of 0 and f of 1 only as calculated, and all the others are not calculated. Okay. Now how the flow happens is, first f of 5 will be called. Okay. It will check whether the f of 5 is already calculated or not. It is not calculated, right? So it is -1. It means what? It is not already calculated. Now what happens is it makes recursive calls f of 4 and f of 3. Okay. So now comes f of 4, right? So it is serial, right? It will not do parallel calculation. It will do a serial once. Only once f of 4 returns some value, it goes to f of 3. Till then, f of 3 will be idle. So first comes f of 4. It will check whether f of 4 is already calculated or not. It is not calculated. So immediately it goes to the next level. It calls f of 3. F of 3 is also not calculated. So comes to f of 2. F of 2 is also not calculated. Now from f of 2, the first recursive call f of 1. F of 1 is already calculated. So what happens? It will return 1. Okay. So from the left hand side, f of 2 has got f of 1 and comes to right hand side. This is also calculated. So 0 will be returned. Now f of 2 has got f of 1 and f of 0. Now what they are going to do is they're going to add these two values and then update in this table and mark it as calculated. Okay, whichever value is not minus 1, it means it is calculated. So f of 2, 0, 1 plus 0 is 1. So it is calculated. First store the value 1 and then a 1 will be returned to f of 3. Now it comes to the right hand side. It sees that it's already calculated. So returns 1. So now f of 3 will be evaluated. Okay, f of 2 plus f of 1. So 1 plus 1 is 2. First update the table and then return it. So for f of 4 from the left hand side you got f of 3. Now then go to the right hand side. F of 2. If you see the table, f of 2 is already calculated, right? So these two recursive calls can be stopped, right? So these two recursive calls can be avoided. Why? Because f of 2 is already calculated. I can take this, refer this table and then pass it. Okay. So now f of 4 is calculated. 2 plus 1 is 3. Update this table and then now you return 3. Now go to f of 5. Now come to the right hand side. F of 3. So f of 3 check in the table. It is already calculated. It will return 2. Now you can see all these recursive calls are avoided. Okay, now f of 3 also will return 2. 3 plus 2 is 5. Now we can return 5 to the main program. So now understood? See how many recursive calls we are avoiding? Okay, so this is just a smaller tree, right? F of 5. Imagine for f of 100. So it's going to be a huge tree and you can imagine how many recursive calls will be avoided. Okay, just by adding a extra additional memory of one linear array. Okay, one normal list we are adding. From this list we can refer and then we are storing all the suboptimal solutions. Okay, so all these are suboptimal solution and this is the solution. Okay, f of I is the answer. Okay, so now did you understand any doubts in this?
No, sir.
Okay, now what is the complexity of this algorithm? What is the complexity of this algorithm? Can you see it is linear? Okay, see every time, okay, only the left recursive call will be called. The right recursive call goes and immediately it returns back. Right? See here, f of 4. It went right. Immediately it checked the table. It is already calculated, so it returns back. Similarly, f of 5 comes to the right hand side. F of 3 is already calculated, so it will return back. Okay, now for f of 6, left is f of I, right hand side would be f of 4. F of 4 is already calculated, right? 3 will be returned. 8. Understood? Okay, so this is linear time. Right hand side recursive calls completely avoided. So without dynamic programming, if you see the solution would take factorial time. Okay. Now it has got reduced to n linear time. Okay. So like for doing this dynamic programming, so now I understood what is dynamic programming. You are storing these suboptimal solutions. See, like every solution is going to be a suboptimal solution. Okay. Suboptimal. Optimal means this is the best answer for two. Okay. Fine. So now let us discuss few problems. Let us discuss Ebox problems itself. 1 minute. So the next first problem in Ebox is the knapsack problem, zero or one knapsack problem. Okay. So let us take the same example that we discussed for greedy strategy and try to solve this using dynamic programming. So in dynamic programming, I told you that we'll be storing the suboptimal solutions, right? So like for storing the suboptimal solutions, you need some storage space, right? So that storage space is either going to be a one-dimensional list or a two-dimensional list. We can also call it as a matrix. Okay. So now let us see an example. This is an example where you're going to use a matrix as a storage structure for storing the suboptimal solutions. Okay. And this is zero or one knapsack problem. So what is zero or one knapsack problem? You have the capacity of the sack, which is 7. Okay. And then you have the set of items and the corresponding weights and the corresponding profits. You need to fill the sack with the items. And the one constraint given here is you cannot take a fraction. Either you can take the entire item or you're going to leave the item. Okay. So that is the constraint here. So now here, we need a two-dimensional array. So the size of the two-dimensional array, that is the number of rows and number of columns, is going to be, so the row count is nothing but the number of items plus 1. Okay, so here there are 4 items, so the number of rows is going to be 5. And number of columns is the weight of the sack plus 1. Okay, so number of rows is 5 and the number of columns is 8. Okay, W plus 1, 7 plus 1, 8. So we're going to construct a 5 cross 8 matrix. Okay. Now the values inside this matrix are going to be the profit values and the suboptimal profit values. Suboptimal profit values in the sense, like suppose if you take this particular cell, okay? So if you're considering only 2 items and if the capacity of the sack is 4, this particular cell will hold the optimal profit in this scenario. The scenario is capacity of the sack is 4 and then only 2 items you are considering. Like that, each and every cell is going to hold the particular profit values. Okay, so in this cell means if the capacity of the sack is 5 and you're considering 4 items. Okay, so actually here 6 are there. Okay, so 5 cross 8. Fine. Okay, so now let us fill this table, and I'll show you how to fill this table. If you take the columns, sorry, rows, so each row is going to correspond the items. So what happens if you take only item 1? What happens if you take first 2 items, 3 items, 4 items? Like that, you're going to take one by one. And the column represents what if the capacitor stack is 0? What if the capacitor stack is 1, 2, 3? Like that, you're going to increase the capacitor stack one by one. Understood? So this is the problem. Okay. Now, so here, first row, if you're not considering any items at all, what is going to be the profit values? I'm not taking any item at all.
0.
Yeah. Only if I take any item, I'll be able to calculate the profit, right? So no items, so profit is also 0. Yeah. Now coming to the first column, that is 0th column. 0th column means what? If the capacity of the sack is 0. If the capacity of the sack is 0, will you be able to place any item?
No.
No, right? So profit?
0.
Yeah. So the first row and first column, you're going to initialize it as 0. And the reason you know. Okay, this it means you're not considering any item in the first row. The first column means if the capacity of the sack is 0. Now let us fill the remaining cells. The first one, 1 cross 1, which means what? We're considering the first item and the capacity of the sack is 1. So if the capacity of the sack is 1, will you be able to place item 1?
No.
No, right? Because the weight of the item is 4, but the capacity is only 1, right? I cannot place. If that is the case, if I'm not able to place a particular item, just take the previous value and put it here. Okay, whatever is the previous profit, the same profit will hold here because I'm not able to place the item. Okay. So if the capacity of the sack is 2, then also I cannot place. If it is 3 also, I cannot place. If it is 4, I can place. Okay.
1.
Yeah. I will place only on a condition. If my current item is giving me more profit than the previous consideration. Okay. So only then I will update this. Else I will take the previous profit itself. Okay. So I have already taken gold. Why would I go for silver? Okay. The same reason. So here, if the previous profit itself is more profitable, then I will not go for the current profit. So now first I have to calculate my current profit. So to calculate the current profit, what you have to do is take the weight of the item. Okay, so like now what you're going to do is like if the current item is 4 kgs, so I should have some 4 kg free space. Then only I'll be able to place the item, right? Okay, so my current item's weight is 4 kgs. Only if I have 4 kgs free space, I'll be able to place the current item. So that one you're going to do. So in the previous row, go 4 kgs before. Okay, and see what is the profit. It is 0. Okay, so add 0 with the current profit. So this was the previous profit by reducing 4 kgs. So now it was 0 and adding the current profit 0 plus 8 is 8. And you can see here I will put 8. Why? Because it is better than the previous profit. My previous profit is only 0, right? My current profit is 8. So I will consider this item. Okay, so this is the procedure. See here, to fill this, so I should remove 4 kgs. After removing 4 kgs, you can see that the profit is 0. 0 plus 8 is 8, better than the previous profit. So 8. Similarly, here also 8, here also 8. Now let us fill the remaining cells and you will understand it better. Now coming over here. Coming to the second row means what? We are considering the second item. And you can see second item's weight is 2. And you can see now the current capacity is 1. So I will not be able to place my second item if the capacity is 1, right? So I'll take the previous profit and put it over here. Now coming over here, I will be able to place the item. Removing 2 kgs, you can see the profit was 0. 0 plus 6 is 6, which is better than my previous profit. So I'm marking it as 6. Tell me what is the value here? What would be the value over here? Hello. Were you able to follow this? See, okay, I'll tell once again. See, I'll tell for this also. Removing 2 kgs. See, I should make 2 kg free space, right? Then I can place this second item. So I am making 2 kgs free. I'm checking for the profit to 0. 0 plus 6 is 6, which is better than the previous profit. So 6. So what about here?
8.
Yeah, correct. 8. Why? Because if I remove 2 kgs, my previous profit is 0. 0 plus 6 is only giving me 6, right? Whereas my previous profit is 8 k 8 profit is 8. So it is better than the present profit. So I'll take that value itself. Now here, remove 2 kgs, 0 plus 6, not better than the previous profit. So I can take the previous profit. What about here? Yes, what?
14.
Yeah, correct. So after removing 2 kgs, it was 8. So 8 plus 6 is 14. So 14 is better than 8. So 14. And here also it is 14. Now coming to the third row. Third row means third item, right? So here, till these two positions, I will not be able to place. So I can take the previous values itself. Now at if the capacitive stack is 3, I'll be able to place the item. So 15, right? So it is better than the previous profit, 15. And what about here?
20.
Why 20?
So we will take the like free up the this previous place, no? 3
Yeah,
places. So it's 12
0.
plus
No?
8. Okay, we have to leave this 3. Okay.
Which 3 you are considering?
8, 6, and 6.
Yeah, these 3 you should remove.
Hmm. Okay, then the remaining is 0.
0. 0 plus 15 is 15.
15.
Okay, here?
6. This also 15.
No,
Hmm.
after removing 3 kgs.
6. 6 you get. 6 we are getting.
Uh, 6
Fif-
plus
15.
15.
21.
Hmm. Better than 8, right? So
Better
21.
than.
Here,
27.
why 27?
So we have removed 4, 14, 8, and 8.
Yeah,
And 6, 6 is remaining. So that's
no,
12.
you should not add this 6 also.
Okay, only one we have to take.
Yeah.
Okay. So then 21 only.
Hmm. Here,
Okay. 23.
yes. Remove 3 kgs, you'll get 8. 8 plus 15 is 23. So 23. And the last row. Here,
0.
no. Here the weight is
weight
1.
is 1 only. Okay.
Okay.
1 0. So we can
So
add
it is 4.
4.
Okay. Here
4 only? No, 6.
6. 4 is the current profit, but the previous profit is 6. Better. So 4. 6, sorry. And here
15.
yes. Okay. The current profit would be 10, right? 6 plus 4 is 10.
Hmm.
But my previous profit is better, so 15. Here
19.
yes, 19. Here
19 again. No, 21.
21. Here
25.
25. Here
25.
yeah, that's all. Okay. So now this particular location is there, right? 4 comma 7. This is the most optimal solution. Okay, this is the highest profit that can be obtained from these items. 25. Now we have found out what is the maximum profit, but we haven't kept track of what items we have considered to get this profit, right? So before going to that, like, is it okay with this? Any doubts? Others? Okay, fine. Yeah. So now we're going to we're going to see how to trace like what all items we have chosen to get this profit. Okay. So for that, what you're going to do is you're going to follow an algorithm. See, start from the last row, last column. Okay. So when can we say that a particular item is considered? Only if it is giving a better profit, right? So if this was also 25, suppose, okay, I'm just simply changing. If this was also 25 and here also you can see it is 25. So what does it mean? It means that simply you've taken the previous profit and put it over here, which also means that you're not considered the current item. So if there is any change in the previous profit and the current profit, it means that you have considered. Okay. So wherever I've considered, I'll mark it as 1. Wherever not considered, I'll mark it as 0. Okay. Now, so after this, after finding that a particular item is considered, go to the immediate before item, that is immediate row, and remove those many kgs of or those many like the weight of the lastly chosen item. See, here we've chosen 4, right? So what is the weight of 4? 1. So what you're going to do is go to the previous row and then remove one weight. Okay, remove one weight means you are reducing 1 kg, going to the previous row, previous column. Now again do the same process. Check whether there is any change. So there is a change, which means that you have considered the item, mark 1, go to the previous row, and then, so what is the weight of the lastly chosen item? 3, right? So go 3 rows before. So come to this particular position. Again do the same process. Check whether there is any difference. Yes, there is a difference. So mark as 1. Go to the previous row. What is the weight? 2, right? So reduce 2 kgs. Come here and check whether there is any difference. No, there is no difference, which means you have not considered item 1. And once you reach row number 0, you can stop the iteration. I'll repeat again. Start from the last row, last column. Okay. So you will know that a particular item is chosen only when there is a difference in the profit. Okay, you have to put a loop and then iterate. Okay, till you find a difference, because you don't know how many items are left out and how many items are chosen. Okay, you have to put a loop and then iterate till you find a difference. Now here itself there is a difference. which means that you have considered that item. Okay, which means that you have considered that item. So if you know that you consider that item, go to the previous row and then reduce as many number of kgs of that particular item. So it is 1 kg. So reduce, go to the previous column. From here, apply the same process. Check whether there is any difference. If there is no difference, again go up. Like that, you keep on going until you find a difference. Here itself, there's a difference. So it means that you have considered item 3 as well. If you have considered that particular item, okay, go to the previous row and then reduce 3 kgs. Do the same process. Check whether there is any difference. Yes, there is a difference. Go to the previous row, remove 2 kgs, check for difference, no difference. So mark 0. And you can see that you have reached row number 0. Understood? Once you reach row 0, you can stop. And these are the, wherever I marked 1, only those items are chosen. Okay, if you just add and see, 6 plus 15 plus 4, you will get 25. Understood? Any doubts in this? Any doubts? Okay. Now next problem. The next problem is longest increasing subsequence. Okay. So this is another interesting problem. The problem says that you'll be given with an array in random order. A random array will be given, and you have to find out the longest increasing subsequence. So what is longest increasing subsequence means? What is increasing subsequence means? See here, you should have a subsequence that is increasing. Suppose you take 3, then 12. Okay, after taking 3 and 12, you cannot take 1 because there's a decrease. So after taking 3 and 12, you can take 23. You cannot take 11. Then you can take 52. Okay, you cannot take 31. Then you can take 61. Okay, then 69, then 70. So this would be an increasing subsequence. Like that, there are a lot of other possibilities also, right? Okay, so you can take 1, 11, 31, 61, 69. Like that you can go. Okay, or you can start from 0, 11, 52, 61, 69. So like that, there will be a lot of combinations of increasing subsequences. Among that, you're going to find out which is the longest increasing subsequence. Okay. So now let us see how to solve this problem. Okay. So let me index all these values. So there are totally 12 numbers. Okay. Index from 0 to 11. Now the procedure is you need to create one array. So I told you for memoization, either you are going to create a one-dimensional array or a two-dimensional array. Right? So this is an example where you're going to use an one-dimensional list. Okay, here I let me call it as array itself. I'm used to that as well. Okay, so one-dimensional array is used to store the suboptimal solutions. Now here, So we haven't started solving, right? So first we need to initialize this table. So what value can be used to initialize this table? Any idea? And what would be the reason for that? As well, you have to give. What can be the initial value? What can we initialize this table as? 0, 1, minus 1, 2. Like what would be like suitable for solving this? And I'll tell you this array is going to store the length.
I think 1, sir.
Okay. Why?
Because only one element is, I mean, we are considering only one element, so it will be the maximum value.
Okay. Very good. So if we take individual elements, okay. So if you take individual elements, what does it mean? It means the length is 1, right? Okay. So considering that before and after the that particular number, there are no numbers at all. Then there is only one element. That is why we'll initialize this entire table as 1. Now the procedure goes like this. So like what you're going to do is, if you take a particular number, you will consider all the previous values, and then among all the previous values, you choose only the values which are less than this particular value. Okay, suppose you're taking 12. So before 12, you will check what all numbers are there. So among all the values which are before 12, you will choose all the lower numbers, smaller numbers than 12. Among all those smaller numbers, you're going to find out which is having the largest LIS. LIS is nothing but longest increasing subsequence. You pick that particular value, add 1 to it, and then store it in that particular index. Okay. So we'll proceed, and then I'll parallelly tell the algorithm and then solve this. So 3 is not having any previous value at all. So there'll be no change here. 12 is having some previous values. Okay. Among these values, only 3 is there. And it is also less than 12. So what he told us, among all the smaller values, you have to choose the largest LIS. There's only one value which is less than 12, and the LIS is 1. So that will be the maximum value, right? So 1 plus 1 is 2. Okay, that would be the corresponding value for 2, LIS value for 12. Now coming to 1. Are there any smaller values than 1? In the left hand side. You're not going to see the right hand side, only the left hand side. So there are no smaller values than 1, right? So if that is the case, then no change. So even for 0, no change. Now coming to 23. So if we see for 23, all the numbers are less than 23, right? So among all these numbers, which number is having the largest LIS? 12. Okay, so 12's LIS is 2. So 2 plus 1 is 3. See, these are all the suboptimal solutions. If you consider only till 23, 3 would be the LIS. Okay, length of the longest increasing subsequence. Okay, and the sequence is going to be 1, 12, and 23. Right? Understood? So that's what you're going to proceed. So like for computing this 3, okay, we did not calculate again, right? We just use the computed value for 12. Okay, we again did not go and check what is the value for 12. So we already calculated for 12. We use that value to compute for 23. Understood? So that is why this is called dynamic programming. Okay, fine. For 11, can you tell me for 11? What is the LAS for 11?
23.
Here, why 23?
Sorry.
No. See, you have to take only the values which are less than 11.
1
Okay,
and 3.
3,
2,
1,
sir.
and 0. Yeah. So we have three numbers which are less than 11. Among those, all the numbers are having only 1 as the value. The maximum itself is 1 only. So 1 plus 1 is 2. So 2 is the answer. So now 52, for 52, what is the answer?
Four.
4. Yes. How 4?
Greatest LS before 11.
Before.
3 for 23 it is 3. So
Okay.
I mean before 52.
For 52. Okay. So we have all these values which are less than 52, and the value that is having the maximum LAS is 23 and the value is 3. So 3 plus 1 is 4. For 31,
4 again.
yes. 61,
5.
5. 69,
6.
6. 70,
7.
7. 2,
2 I think. 3 3. 2 2.
2 only. So
Yeah.
yeah, there is only one value less than 2. Sorry, two values are there. Among those two values, both are having 1 only. So largest is also 1. 1 plus 1 is 2. So now you got this array LIS, okay, for all the elements. Now the largest value in this particular table will give you the answer. Okay. So 7 is the length of the longest increasing subsequence. Now the question is, how will you find out what all elements you have considered to get this count 7? You haven't kept track of that, right? So for that, what can we do? What can we do to keep track of what are elements we have considered, or is there any other algorithm like we did for knapsack problem to trace whatever items will come under that sequence? Okay, so actually there's an algorithm to do that. So what we're going to do is we're going to keep track of the parent of each element from where it was derived from. Okay, that particular thing we'll keep track of. So this array is going to hold the index of the number from where it was derived from. See, for example, let us take this 2. So this 2 was derived from 1, right? So what is 1's index? 1's index is 2, sorry, here. So 1's index is 2. So that this particular index would be stored over here. So like that, you're going to store all the index values of the previous elements. Okay. Now
Once
what?
again.
Yeah. See here, this particular array is going to store the index of the parent. Parent in the sense from where this particular element was derived from. Okay, so if we take, for example, this 52. So 52, the answer is 4, right? So how did we get this 4? We took the value from 23 and then added 1 and then stored in the place of 52, right? So which means what? 52 was derived from 23. So we'll store 23's index, which is 4, at 52's position. So which means what? 52 was derived from the element at 4th index, just 23. Okay.
Okay.
Yeah. So what should be the initial value of this parent array? You're going to store index, right? So what should be the initial value?
0.
0. No, not 0. Why not 0? Because 0 is a valid index. Then what happens for every value? Then 0 will be considered as a parent. There are few elements which doesn't have parent, right? 3 doesn't have a parent, 1 doesn't have a parent, 0 doesn't have a parent. So you cannot say that 3 is a parent of 1 and 3, 1 and 0 and that. Understood? Okay. So what should be the value? We have to give one invalid index. -1. Any negative value can be given. By default, let us have it -1. So -1 is an invalid index, right? Understood why -1? Because this is not a valid index. Okay. So now 1 is not 3, okay, doesn't have any parent, so it can be -1 itself. So for 12, 3 was the parent, right? So 3's index is 0. So at this location, change it to 0. For 1, no parent, so -1. 0 also no parent, -1. 23 was derived from 12. So 12's index is 1. So store 1 here. Okay. So tell me what should be stored in. Okay. For 11, you can see there are 3 elements which can be considered. So all those 3 are 1 only. And the smaller values, sorry, the largest value is also 1. So in that case, if we have multiple options, choose the first option. Okay, don't get confused. Just choose the first option.
First in the sense largest, sir.
No, not largest. The first value. See here, 1, 1, 1. Okay, 3 ones are there. All the 3 ones are maximum only. So whichever is coming first.
Okay.
Okay. So 3 is index is 0. So that would be the parent for 11. For 52, what is the value? Parent value?
4.
4. It was derived from 23. 23's index is 4. So 4. Good. 31.
Same 4.
Yes. 61.
6.
Yes. 52's index 6. Okay. So 6 here. 69.
8.
8. 70.
9.
9. 2.
And 2 is 1. 2.
2. 2 was derived from 1. 1's index is 2. So 2 here. That's all. So with this array, we can track what all elements we have considered. How to track is that, okay, 7 is the largest value. Okay, just trace this table, maximum value in this table, give you the length of the maximum longest increasing subsequence, which is 7. So the corresponding element is there, 70, and its parent is also there. Okay, so just note on all the elements, 70. So now go to its parent. So parent's index is 9. So go to 9th index. The element is 69. 69's parent is 8. Okay, 8, the value is 61. 61's parent is 6. 6, the value is 52. 52's parent is 4. 4's value is 23. 23's parent is 1. 1's value is 12. And 12's parent is 0. 0's value is 3. And 3's parent is -1. Okay, you will keep on proceeding till you reach -1. So 3 doesn't have a parent, right? Okay, so we'll go till this point. So now these are the values which will come under this LIS, longest increasing subsequence. Understood? Any doubts in this?
So,
Yeah.
can you explain the reason that initially in LIS, why did you take all as one? That I have not followed.
Okay. See, actually, if there is only one element in the array, then LIS is one only, right? Okay, so we're going to take the previous value and then add it like so considering that no elements before this particular element are less than that particular element, then what happens? That would form the maximum. See, we are not doing any processing at all. We have to just do an initialization. Okay, so like for that purpose, like either you can take it in both the ways. One is that if there is only one element, then that is going to be the largest increase in subsequence. Or you can also consider that if all the elements are less than, all the elements are greater than the particular element, okay, which element you're considering, then also the answer is going to be one only, right?
Okay.
So is it confusing? See, actually, like, so you can take the first itself. So if there is only one element, then that is going to be the longest increasing subsequence, right? Largest increasing subsequence. Okay.
Okay.
So yeah. So this is how you will find the maximum length of the longest increasing subsequence, and this is how you will keep track of what are elements will come under that. So this algorithm is suitable only to find a single solution. So there might be multiple solutions also, right? So in that case, we cannot use this algorithm. We have to go for either backtracking or branching bound. Okay, this algorithm will give you a single solution. So if single solution is sufficient, then this you can use this algorithm. Okay, fine. So let us see the next algorithm. The next algorithm is the longest common subsequence. Okay, so the longest common subsequence means what is like so you know what is a subsequence from the previous problem itself. You would have come to know what is a subsequence. So from a sequence, you're taking a few elements in the same order. Okay, then you will get a subsequence. So here also longest common subsequence means, see here A, okay, A, D, F, D. Okay, here also ADFD is there. Here also ADFD is there. So that is called common subsequence. Like that, you might have a lot of common subsequences, right? Okay. So C, D, F. Okay, you also have C, D, F, D. That is another subsequence. Like that, among all the subsequences, common subsequences, you're going to find out the longest common subsequence. So this problem, we're going to make use of a two-dimensional array to solve. Okay. This is string 1, string 2. Okay, this is string 1 and string 2. Now we're going to create a two-dimensional array, and the size of the two-dimensional array is going to be the number of characters in string 1. So number of characters in string 1 plus 1, okay, cross number of characters in string 2 plus 1. Understood? Okay, so plus 1 y means like we have to do some initialization, right? So the same thing we've done in knapsack problem also. For that process only plus 1 is coming. So length of string 1 plus 1, length of string 2 plus 1. So length of string 1 is what? 6. So number of rows is 7. Okay. Number of columns is 1, 2, 3, 4, 5, 6, 7, 9. Length of string 2 plus 1. Now we're going to construct a 7 cross 9 matrix. Here, these are going to be indices only. Just for simplicity, for like easy understanding, I write the characters itself. Zero. The characters. Okay, fine. So if you are not considering any character at all in string 1, so the length is all going to be 0. Here also 0. First row, first column, 0. Why? Because not considering any character. So from we need a starting point, right? Okay, that's why we are marking everything as 0. The first row and first column. No. So there are two cases. One is if these two characters match. Okay, what is the scenario? Like what should we do? And if these two characters does not match, what we should do? Okay. First, if they are not matching, you have three possible solutions, right? So you have three adjacent values. One is the left one, top one, and the diagonally top one in the left hand side. Top left, you can also say. Left, top, and then top left. Among these three, whichever is giving you the maximum value, that can be taken here. Okay, fine. So if they are not matching, if they are matching, the previous diagonal value will have the optimal solution. So plus 1, you can take it as the current value. So we'll fill this table, you will understand. So here they are not matching. So among these three values, the maximum is 0 only. So we can take that itself 0. Here A and A are matching. If both are matching, what you should do is just take the top left value, the diagonally present value, and then add 1 to it and then store it here. Understood? If they are matching, diagonally top left plus 1 will give you the value. So here A and D, they are not matching. So among these three, the maximum value is 1. So 1 is the answer here. So here also, not matching. A and D not matching. So among these three, maximum is 1. So 1. So what is the value here?
1.
1.
1.
Here, AD
1.
1. AL
1.
1. AA
Here also 1.
0. 0.
no.
1.
Why 0?
Diagonal you said. You said
Diagonal?
diagonal. No?
Plus
Yeah,
1.
diagonal plus 1 I told, right?
Okay. Okay.
Okay, so both are matching. So diagonal plus 1. So here, CC
1.
1. CA
1.
yeah 1. Not matching. So maximum among these is 1 only. CD
1.
1. CE
1.
1. CF 1.
1. All
Nothing
1.
is matching, all 1. DC
1.
1. DA 1.
1.
DD
2.
2. Okay, so diagonal value plus 1. DE
1.
no
2. 2.
2.
Sorry.
2.
2.
DF
2.
2.
DD
2.
yes. Diagonal value is 1 only, right? So plus 1 is 2. DL
2.
2. DA also.
2.
GC
1.
1. GA
1.
GD
2.
2. GE
2.
2. 2. 2. 2. 2.
2. 2 only.
All are 2. DC
1,
1, DA
1,
1, DD
2,
matching, so diagonal value plus 1, 2. DE
2,
DF DF
DF also 2,
2, DD
3,
3. Yeah. So DL and DA 3,
3,
3. So H not matching, so the same
1.
1, 1, 2, 2, 2, 3, 3, 3. Okay. So this is how you will formulate this. The 3, why 3, 4, no? A, D, okay, 3 only. A, D, D. So here also, how come here 4? Did I miss anything? A, D, F. I think I missed F. Okay. Instead of
Yes, in this we have 1 F also.
D,
In the
F.
rows.
Instead of G, I put F. Sorry. Instead of F, I put G. Okay. So let us do this again. Last 3 around. Okay. By mistake, instead of F, I put G. So now F 0. Also 0, 0. Okay. FC 1.
1,
FA 1. FD
2,
2,
2. FE
2,
2,
FF.
3,
Okay. FD
3 again.
3,
3,
3, 3.
3,
Now D. DA
1,
DC 1.
DC 1,
DA also
1,
1. DD
2,
2. DE
2,
2. DF
2,
3,
3. 3.
3, 3,
DD now
4.
4. Okay. Diagonal value is 3 plus 1, 4. 4, 4. Now, all previous values 1, 1, 2, 2, 3, 4, 4, 4. Okay. So the last values are right. This will give you the optimal solution. Okay. So this is the length of the longest increasing subsequence. Now I'll give you a task. You're going to find out what is the procedure to find what all items or what all characters are chosen to get this longest increasing, the longest common subsequence. Okay. So you need to find out the algorithm to trace the longest common subsequence. Fine. Understood this, right? See, only 2 conditions. If they are matching, take the diagonal value, add 1 and store it in the current location. If they're not matching, you have 3 adjacent values. Among these 3 adjacent values, whichever is the maximum, take that and store it in the corresponding location. That's all. Now let us see the last problem. All pair shortest path algorithm. Okay. So give me a minute. I'll just take an example. Okay. So in this all pair shortest path algorithm, you will be given as a directed weighted graph. Okay. So you have a directed graph. Directed means, right? So from 4 you can travel to 2, whereas from 2 you cannot travel to 4. So you have a directed weighted graph. It might be an undirected graph also. Okay, you will also be given the directed graph also. So if it is, okay, I'll tell you what happens if it is a undirected graph. Okay, once we complete this algorithm, I'll tell you. So, and definitely it's going to be a weighted graph. Okay, why? Because the problem itself is shortest path, right? To find it is something related to length, right? So if length itself is not given, then we'll not be able to find out which is the shortest. So definitely it's going to be a weighted graph, and you're going to find the various path. Okay, so all pair means what? So for you're going to consider all the different pairs. So 2 to 4, okay, 4 to 2, 3 to 4, 4 to 3, 1 to 4, 4 to 1, like that. So whatever possible pairs are there, all possible pairs you're going to consider, and then you're going to find out the shortest path among between the two pairs. Okay. Now I'll I'll simply give an example here. See, if you see from 1 to 3, there is a direct path which is 9. But if you travel through 2, okay, so you have an alternate path via 2. So 2 to 1, sorry, 1 to 2, and then 2 to 3. So it takes only 6 length, right? So which is better than the current length. So what happens? This will be the updated length. Okay, likewise, if you see from 1 to 4, there is no direct length. Okay, if you go through 3, what happens? You'll have a length of 11. Whereas if you go through 2 and to 3 and to 4, then you'll have a better length. Okay, better shorter length. So which would be 6 plus 2, 8. Understood? Right? So this is what is the algorithm. You're going to find out the length of uh, the path between each pair of the nodes. So for this, we're going to construct a matrix, and that matrix is going to be the number of vertices cross number of vertices. So here there are 4 vertices. So it's going to be a 4 cross 4 matrix. The algorithm is very, very short and very simple. The tracing takes a lot of time, okay, to understand. So we're not going to trace it completely. You'll just understand how this is working. And then we'll see. So these are the node numbers. Okay, so here it is 1, 2, 3, 4. So let me write 1, 2, 3, 4 itself. Actually, index is 1, 0, 1, 2, 3 only. Since the vertex values are given as 1, 2, 3, 4, I'm marking it as 1, 2, 3, 4. And in this problem, we are going to consider, okay, so if it is the same node, 1 to 1, the distance is going to be 0. Okay. Why? Because if we write it as infinity, if you mark it as -1, what happens? It will start calculating the value for 1 to 1 also. I don't want that to happen because I already know that I'm already in 1 only. So why should I go back again to 1? Okay. So why should I go to 1 by choosing some other path? Okay, that is not correct, right? So I'm already 1. Why should I take an alternate path and go there and then come back to 1? So you mark it as 0. So that is why certain problems needs this diagonal to be initialized as -1, that is infinity, and certain problems need to be initialized as 0. So this problem you will initialize it as 0. And fill all the distance values. So 1 to 2, 5, 1 to 3, 9. 1 to 4, no path, so -1. We are assuming that there is no negative weights. Okay, negative weights are not there. So 2 to 1, 2 to 1, there is no path, right? So -1. 2 to 3, 1. 2 to 4, no direct path, so -1. 3 to 1, there is no path. Only from 1 to 3 there is path. 3 to 1 there is no path. So -1. 3 to 2, no direct path. So -1. 3 to 4, 2. 4 to 1, no direct path. So -1. 4 to 2, 3. 4 to 3, no direct path. -1. Yeah, that's it. So this is the initialization that we have to do for this problem. Okay. Just having the graph. Taking the graph in the matrix representation itself is the initialization for this problem. Now we are going to update this table. How we are going to update this is, so this is a bit lengthy process, but still we'll understand how it is done. So we are going to take ISD. Okay, so just keep this in mind, ISD. So ISD is nothing but intermediate source destination. Okay, intermediate source destination. So now what we're going to do is we're going to start from the source, go to the intermediate, and go to destination. So start from the source, go to the intermediate, and then reach the destination. So this is going to be the process. And we're going to find for all the possible combinations. Okay, so there are 4 nodes. So we are going to write all the possible combinations over here. So 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 1, 4. Now 1, 2, 1, 1, 2, 2, 1, 2, 3, 1, 2, 4. And now 1, 3, 1, 1, 3, 2, 1, 3, 3, 1, 3, 4. And then 1, 4, 1, 1, 4, 2, 1,
4, 3.
1, 4, 3, 1, 4, 4. So this is for one series. Similarly, we have for 2 series, 3 series, 4 series. Okay. Now let us do this one series and then you can go for 2 series first. See, what does this particular state 1, 1, 1, 1 mean? It doesn't make any sense, but still I'll tell. So starting from source node 1, you're going to the intermediate node 1 and reaching destination 1. Okay, so let us take 3 different values. Okay, see here 1, 2, and 3. This means what? From 2, you're going to 1, and then from 1, you're reaching 3. Okay, so you will calculate this path if this path is giving you a better solution than the direct path. For 2 to 3, you would have already calculated, right? See, for 2 to 3, already have a direct path which gives the value as 1. So you're checking whether an alternate path gives a better solution.
So,
Yes.
so in this question, 2 to 1 doesn't have any path.
No, 2 to 3. So I'm checking for direct path first.
Okay.
Okay. 2 to 3, that's a direct path. I'm checking whether this alternate path will give a better solution or not. See, the alternate path is 2 to 1 and then 1 to 3. So 2 to 1 itself, there is no path, right? So it's not going to give a better solution. So the same value will be there. Okay. So like that, we'll keep on updating this table for all the possible combinations. Then finally, you'll get the answer. Finally, this table will contain, right? Okay. So that final configuration would be the shortest path within each pass. And you can see you have all the combinations, all the possible pairs are here. Okay, fine. So which, if there are two values which are same in this ISD, then you can simply skip that. Why? Because the same value itself will be the best solution. Okay, I'll repeat again. If you have any two values same, either I and S same or S and D same or I and D same, so no need to calculate at all. Okay, why? Because one thing is it will not make any sense, or it will go to an alternate path and reach the same node. For example, here. Okay, so here source and destination are same. So now what you're doing is from 2 you're going to 1 and then reaching to 2. Okay, so for these cases you need not consider at all. See, in this case intermediate and destination are same. Okay, so going from source to intermediate and then intermediate destination and destination are same. It is like going directly to the destination, right? So if any two values are same, then no need to worry at all. So it will be the same. So these four cases we can simply avoid. Okay, so it will be the same values. So here 1 and 1 are same. So this also can be avoided. This also can be avoided. And here 1, 2 and 3. So we can also avoid if any of the path is having an infinite value. No, don't do that. Don't do that. See here. So here from source to destination, right? So source to destination is giving an infinity. Okay, infinity plus 1 to 3. Already it gave infinity, so it is not going to be better solution. So this can be, there will be no change here. And here also the same case. 2 to 1 it is infinity. So there will be not any change. Okay. So this can be avoided because intermediate and destination are same. And coming over here, 3 to 2. What is the direct path? There is no direct path, 3 to 2. We are checking whether any alternate path is there. So from 3 to 1, that also doesn't have any path. So this also no change. Here, the source and destination are same, so no change. Coming here, 3 to 4 and 3 to 1, there is no path, right? So anyway, this is also not going to affect at all because alternate path is not there. Okay. Now coming here. So this doesn't make any sense because intermediate and destination are same. And here 1 to 4. See here also 1 to 4 it is infinity. Okay, there's no path between 4 to 1, sorry, not 1 to 4, 4 to 1. There's no path. So this also is not going to affect. Okay, so in this first series, there is no change at all. Now let us go to the second series. So here source and destination are same, so no change. Here intermediate and destination are same, so no change. And coming over here. So 1 to 3, okay, 1 to 3, the path is 9. Okay, so we are finding for alternate path. So 1 to 2, okay, so 1 to 2, the path is 5. And from 2 to 3, 2 to 3, the path is 1. So what is the total length? 5 plus 1, 6. Okay. So the previous value was 9. Now the current value is 6, which is better, right? So I can update this. So I'm just giving a slash and then writing just to keep track of what are values like that. Understood? Previously it was 6. Now 9 it got updated to 6 in this step. Okay. So like this here 1 to 4, there's no direct path. We're checking whether any alternate path is there. So 1 to 2 is 5. 2 to 4 minus 1. There is no path. Okay. So we cannot reach through 2 also. So no change. And these four cases, there will not be any change. And here 3 to 1, there is no direct path. We are checking whether any alternate path is there. 3 to 2, 3 to 2 also there is no path. So This is also no change. Here source and destination is the same, no change. Here also there will not be any change because 3 to 2, there is no path. Coming here, 4 to 1, it is infinity. We are checking whether alternate path is there. So 4 to 2, it is 3. And then 2 to 1, there is no path. Okay, so no change here also. And here also there will not be any change because intermediate destination are same. And here 2, 4, 3. 4 to 3, it is infinity. Okay, 4 to 2, it is 3. Okay, and then 3 to 2, sorry, 2 to 3, 1. 1. So 3 plus 1 is 4. And 4 to 3, there is no direct path. So 4 can be the answer. Just a minute, it got stuck. Understood, right? See here, like every time there might be multiple updations also over here. Okay, so even if there is any other shortest path, then that will be updated here. There can be multiple updations also. So like how this is dynamic programming is that, see, from 1 to 4, okay, so from 1 to 4, now what, um, yeah, so from 1 to 4, if we go through 3, so we have already calculated the updated path for 1 to 3, right? So from 1 to 3, it is, there is a direct path, it got updated to 6, right? So we are not calculating this path once again and then finding it to 3, to 4, right? We already calculated for 1 to 3, the optimal path is 6. We are making use of that and then finding out the path to 4. So that is why this is dynamic programming. Okay. Just a mistake. Give me a minute. So this we updated it to
6.
6, and this minus 1 to
4.
4, right? This is what, 2 to 3, sorry, 4 to 3. Okay, to this point it is done. Now this is not going to make any sense. Source and destination are same. So likewise, so let us quickly complete this. Now for 3 series. Okay, for 3 series, if you see, this is not going to work. And here 1 to 2 through 3. Okay, so 1 to 2 is 5. So 1 to 3 is minus 1, there's no path. So 1 to 3, there's no path, right? So all these three is not going to work. And here 2 to 3, there is path. So we can consider this. Okay, so 2 to 1, there is no path. Through 3, let us see whether there's any path. 2 to 3, it is 1. Whereas from 3 to 1, there is no path. So this is not going to work. This also we can avoid. This also can be avoided. And here 2 to 4, infinity. Okay. So 2 to 3, 1. And then 3 to 4, 2. Okay. So 1 plus 2 is 3. So 2 to 4 can be updated as 3. Let us check here also. So 2 to 4. Yeah. So 2 to 4, there is no direct path. So through 3, we can reach 4. And the total is 3. Okay. So 2 to 4 is done. Now, these 4 no need to work at all. 4 to 1. Okay. 4 to 1 is minus 1. So 4 to 3. Okay. 4 to 3 is 4. And then 3 to 1, it is infinity. So no direct path. No path. 4 to 2. It's already 3. Okay. And then 4 to 3 is 4. So it is going to be a larger path only. So it's not going to lead the solution. 4 to 3, 4. Okay, so these two need not work at all. Because in this case, I and D are same. In this case, S and D are same. Now the last iteration. The 4 series. So this can be left. So 4, 1, 2. So 1 to 2 is 5. So 1 to 4 minus 1, no path. So these 4 can be omitted because no direct path from 1 to 4. 4 to 1. So 2 to 1 is infinity. 2 to 4 is 3. And 4 to 1, it is infinity. So no path. So 4 to 2 we need not work out. 4 to 3. 2 to 3 is already 1. Okay. 2 to 4 is 3. Anyway, it will lead a larger solution. So it is not going to give. And this also can be omitted. And coming here. 4, 3, 1. 3, 1. 3
No
to 1,
path.
it is minus 1, no path. 4 to 3, sorry, 3 to 4
2.
is 2. And then 4 to 1, no path. So no change here. 3 to 2, no path. 3 to 4, 2. 4 to 2, 3. Okay, 2 plus 3, 5. So 3 to 2, the answer is 5. Okay, we can also check 3 to 2. Okay, 3 to 2, there's no direct path, so we're going through 4. 3 to 3, no need to work out. 3 to 4 also no need to work out. And these 4, intermediate and source are same, so no need to work out. So this is the final table. Understood? Okay, so this is the trace out of the algorithm. Okay, if you see the algorithm, it is very simple. Okay, so why? Because you can get all these combinations by putting a nested loops, right? Just by putting 3 nested loops, we can get these combinations, all these combinations. So in the problem description itself, the algorithm is given. No need to worry about that at all. See here. Okay, so I'll just simply explain this. See here, you have you're creating an array where you're initializing this array. This is going to be the final matrix. Okay. So like here, cost is the matrix that you are, this is the input matrix. Okay. And you're creating a copy of that. Okay. That is stored in EA. So this is the array in which you're going to update and see how the nested loop. So here K is the intermediate. I told ISD, right? Okay. ISD, intermediate source destination. So K is the intermediate, I is the source, J is the destination. Okay. You see here this logic. So what they're doing is they're taking the minimum of A of IJ. Okay. A of IJ is what? Which is the direct path. Understood? So this is direct path. They're checking whether direct path, checking between the direct path and the alternate path. So this is the alternate path. So here what they're doing is they are starting from source, going to the destination, going to the intermediate, and from intermediate they're going to the destination. Okay, source to intermediate, intermediate to just destination. If this is better than this A of ij, they store that. So which among these two is better? They'll store it in A of ij. That's all. Just 6 lines of code. Okay, fine. Now again, in this problem also, we were able to find out what are the shortest paths, length of the shortest path. Here also we didn't trace what are the shortest paths, right? So um, so from 1 to 4, okay, so from 1 to 4, not 1 to 4, yeah. Why this didn't get updated? I think somewhere I missed. Here I missed it here. 1 to 4, 1 to 3, 6, and 3 to 4 is 2. 6 plus 2 is 8 only, right? This should be updated as 8. I don't know. I think somehow I missed this. Okay. So you know this 8, right? So now you don't know how we reach this 8. That path also has to be tracked, right? So there are multiple paths here. Which path is leading to 8? That also you have to track. So this is also going to be your assignment. Okay. So this is all about dynamic programming. I hope you understood what is dynamic programming. And like the basic idea is you're going to store the suboptimal solution and use that to solve the current solution, obtain the current solution. Okay. So now, like this dynamic programming is very, very important topic because in most of the competitive programs, this is going to be a great help. Why? Because this takes like just this in at the start of the algorithm session, we discuss about the time space trade-off, right? Okay. So that holds here. So with some additional memory, we are going to save a lot of time. Okay, the repeated calculations and all can be avoided in okay in a very huge amount of, by a very huge factor we can avoid. Okay, a very basic example is that Fibonacci series. Okay, imagine a tree for 100, how the branches got cut down, and then you got it as a linear algorithm. Okay, likewise, if you just imagine what would happen for all the problems that we discussed. Okay, so again, this is going to be the dynamic programming solution itself is order of n cube, right? You're putting 3 nested loops. Imagine how the normal solution would be. Okay. Likewise for all these problems. These are all combination problems. Combination problems itself means that it is going to take factorial time. Okay. So a factorial problem has got reduced to what? Length of S1 into length of S2. This also. We have to find all the combinations and then we have to find out the sum, not sum, whether they're increasing or not. Okay. The brute force approach for this problem is what? You're going to find out all the different combinations and check whether which are all the combinations that are increasing, and among all those increasing combinations you're going to find out which is the maximum. Again, this is a factorial problem. Okay, so this is the advantage of using dynamic programming, and this is very important algorithm with respect to any competitive exam you attend. Even if you take an interview for a product based company, this they'll be considering a lot. Okay, fine. So in the next class, we'll see about backtracking and branch and bound. Any doubts in dynamic programming?
No, sir.
Okay. Okay, fine. So thank you. We can wind up today. We can meet in the next class.
Thank you, sir.